It's a great pleasure to introduce Anne Moreau from Orsay, currently on vacation. And she will be speaking about chiral symplectic leaves, arc spaces, and vertex algebras.
Okay, thank you very much for the invitation. So I don't know so much the audience, so please feel free to interrupt me whenever you feel like. So indeed, I'm talking about this topic. So more precisely, I would like to, the aim of my talk is to present the notion of chiral symplectic leaves that we introduced with Arakawa. And there are some vertex analogs of symplectic leaves, but for Poisson vertex algebras. And typical example of vertex Poisson algebras come from arc spaces of Poisson varieties. So this is the first aim, so to introduce the notion of chiral symplectic leaves. So as I said, there are vertex analog of symplectic leaves. And then to give application to general vertex algebra, which are not necessarily Poisson. Application to vertex algebras, and also in particular to W-algebras at critical level, which are some interesting chiral quantization of Slodowy slices. I will explain this later. But first of all, to motivate a little bit this chiral symplectic leaves, I would like to draw a kind of picture, diagram, let's say diagram. So, okay, so if you start with a vertex algebra, an arbitrary vertex algebra, I'm not sure you are familiar with this, but this is a complicated algebraic structure. So let's say here you have category of vertex algebra. You can attach to such a V in a canonical way, several simpler objects. So first of all, any vertex algebra is canonically filtered, and the corresponding graded algebra, graded space, is a Poisson vertex algebra. Poisson vertex algebras. So what it is, so first of all, it is a commutative vertex algebra. So that is to say, differential algebra. So a commutative algebra together with a derivation. And then it has a richer structure of Poisson vertex algebra. So somehow there are infinitely many Poisson brackets. So then you get something easier because it's commutative, but still not Noetherian. And then there is another canonical object you can define from this vertex algebra, which is obtained by taking a quotient of this vertex algebra. And here you get the usual Poisson algebra. So this is a certain quotient of V. So usually the space by which you divide is called C2V, it doesn't matter. This is called a zoo C2 algebra, and this is a Poisson algebra, in general, finitely generated. Okay, so this is a much easier object to study. And lastly, I'm not going to use this in this talk, but maybe I would like to mention that also what you can do, also by considering a canonical quotient, you can use a zoo functor, which sends to any vertex algebra, the so-called zoos algebra, which is here filtered, non-associative, usually non-commutative, associative algebra, unital algebra. And sorry, my diagram is not, maybe I write here. Okay, and this one is filtered, and the corresponding graded algebra is commutative. So that the corresponding graded algebra has a natural Poisson algebra structure. So you can close the diagram like this by considering the graded algebra. And here you can also consider the zoo C2 functor. Okay, so in general, the whole diagram does not commute, which means that here Gr of zoo V does not coincide with RV in general, but still you have this picture. Here this part commutes. All right. Okay, so you have this picture, and what I want to say is that on the right-hand side of the diagram, you have commutative object, and then you can consider the corresponding schemes. So you have geometrical objects, and the idea is that these objects capture some information about your vertex algebra. So here you have the commutative world, commutative algebra, and here you have the non-commutative world. And on the bottom, you have the finite dimensional worlds, if you like, and then on the top, it's an infinite dimensional setting. So here, the object we are going to consider is the scheme associated to RV, which is a Poisson variety, and then the Poisson scheme, and then the scheme associated to Gr V, which is a Poisson vertex algebra scheme. All right, so maybe just to finish this motivation, I just give one example for those who know. I'm not sure how you are familiar, but here, for instance, if V is a universal affine vertex algebra associated with a simple Lie algebra, what are the corresponding objects you get? So for the zoo, you get the enveloping algebra of G, which is, it is known that this is filtered by the PBW filtration. And here what you get is the symmetric algebra of G with the constant Kirillov-Sourayyo-Poisson structure. And here the diagram commute. So this means the quotient here leads also to this Poisson algebra. And here what you get is the coordinate ring of the arc space of G star, of the dual of G. And this is canonically isomorphic to the symmetric algebra T-1, GT-1. So here you get a coordinate ring of jet of something. I will go back to this notion later. All right. So, okay, as you can expect, this quotient RV, by considering this, you lose many information about your vertex algebra, because when you take the quotient, of course, you lose many information. And sometimes it's not enough to consider the scheme associated to RV or RV itself to understand V. And sometimes you like to consider Gr V instead. So it's natural to try to upgrade some notion useful in a Poisson algebra setting to upgrade this in the Poisson vertex algebra setting. So this is what we do, and I will try to give some applications. All right, so let me explain the definition of Chiral symplectic leaves now. Okay, so for the moment, let's consider X to be an affine Poisson scheme, let's say reduced for simplicity. Affine Poisson reduced scheme. So in other words, R is a coordinate ring of X, and it is Poisson. And then since X is Poisson, X is stratified by symplectic leaves. So this is a stratification by symplectic leaves. So it is well known that this is connected. So this I denoted by LX, so symplectic leaf passing through X. So this is a connected smooth symplectic subset of X, but which is not necessarily algebraic. So I mean by that, it's not Zariski locally closed in general. And for this reason, this notion is not easy to upgrade in the setting of vertex algebra, because as I said, it's purely algebraic. So instead, I would like to consider the notion of the notion of symplectic cores, which is slightly different notion. Sometimes they coincide. So let me recall what is a symplectic cores. So the symplectic cores. So here you have another stratification like this. I did not by maybe calligraphic C, the symplectic cores. And here X is in X, but I like to write as a maximal spectrum of X. And then what is a CX? This is the equivalence class of X with respect for the following equivalence relation. We say that X and Y are related if the Poisson cores, I will say in 1 second what it is, of the maximal ideal associated with X is the same as the one associated with Y. So Mx here is the maximal ideal corresponding to X. And what is Pi? So in fact, for all Poisson ideal I, Pi is by definition the biggest Poisson ideal of R contained in R. Okay, so here this is the biggest Poisson ideal contained in the maximal ideal of X. So this gives you an equivalent class, and by definition, the symplectic cores are the equivalent class. So here, actually, CX is not necessarily locally closed as well. But as you see, the definition is more algebraic, and moreover, we have that, in fact, the closure of this is exactly the zero locus of this Poisson ideal. All right, and second, this is smooth in its Zariski closure. All right, and now we have a very nice theorem by Brown and Gordon, which give sufficient condition for that symplectic cores are actually algebraic and also coincide with symplectic leaves. So the theorem says the following. It says that if X has finitely many symplectic leaves, then for all X, the symplectic leaf passing through X coincide with its symplectic cores, and moreover, C or X, which is L of X, is locally closed. So this result has important application, in particular in representation theory. And
there's a question in chat about the definition of the Poisson core. Does I have to be a Poisson ideal?
Sorry, I don't see the chat in this way. So
Dima asked the question. So I does not have to be a Poisson ideal. Otherwise, P of I equals I.
Sorry. I no need to be Poisson. Yeah, of course. Sorry. Yeah. Sorry. For all ideal I. Sorry. Mm-hmm.
And maybe I was going to ask, can you give some feeling for this notion of Poisson core? What does it mean, for example, if the Poisson manifold is a dual of a Lie algebra?
For Lie algebra, it coincides with co-adjoint orbits. The two notions, as I say, the theorem of Brown-Gordon is a sufficient condition, but you may have they coincide even if there is no finitely many symplectic leaves, and the feeling is that it is expected. How I can say so it is expected that it is the finest possible algebraic stratification in which the Hamiltonian vector fields are tangent. But this is not really proved, but this is a feeling of the construction.
Can I jump in and ask maybe the same question in a different way? Can you give an example of a symplectic leaf which is not algebraic?
Yeah, I can give yeah symplectic leaves which are not algebraic. It is what you want. Hmm?
Yes. Yes.
Yeah, I can. Okay, if you, I don't know by heart, but it's not so trivial. But yes, I have some. Yeah, I think. Yeah, I have one example here. So. Yeah, so yeah, I can give an example if I am correct. I think this example is, okay, it does not matter where it comes from, but you consider the algebra. This one with bracket is like this. This is 0. Xz is just alpha x. For instance, for the moment, alpha is in real, and then yz is just y for some alpha in real alpha. And then you can make some calculation, and then you have symplectic leaves fall into two families. So you have the simple points of the form, let's say this, something like this. And you have also set defined by some equation like this. And then now if alpha is a rational leaves, symplectic leaves are algebraic, but if alpha is not rational, then it's not algebraic. But in this example, it's nice because symplectic cores are algebraic. So I don't know how much you want details.
Wonderful, thank you. That's beautiful. Yeah, that's great.
But you see, it's quite most of classical cases they coincide. Yeah. And you have always an inclusion, so between the stratification. So this is okay. So maybe I conclude the example. Okay, so the conclusion is that if alpha is not rational, symplectic leaves are not algebraic, but symplectic cores are. But more, what I don't know if example where symplectic cores are not algebraic as well. So
Excuse
this I don't.
I'm sorry. Could you say briefly what the symplectic cores are in this example?
So I think, but I haven't checked for a long time. I think. Yeah, I think symplectic cores, I think you still have this first family, but then you have something which is algebraic to C star square times C, but I forgot why, but I think this is a conclusion. While symplectic leaves here, you get something, yeah, because yeah, as I say, symplectic leaves, the second family is not algebraic, but in this case, the second should be something like that. Yeah. Yeah. Yeah, this is a symplectic cores, but yeah.
Thank you.
Yeah. Yeah, so the definition, what is nice is, as I say, you can extend to, it's really algebraic definition. So in some sense, you don't need so much material to define it. So that's why we can extend in our setting. But before that, I would like to give an application of that result, namely the fact that with this assumption of finitely many symplectic leaves, symplectic leaves are actually locally closed. And also in this case, irreducible component are just symplectic leaves closure. So the application is due to Ginzburg. So I would like to state like this. So let A be a filtered associative algebra. So for instance, the enveloping algebra of Lie algebra, such that the corresponding graded algebra is commutative, and more specifically, it is the coordinate ring of some reduced scheme. But here I assume is finitely generated commutative algebra with reduced, with no zero divisor. And then, as I mentioned before, this implies that X is Poisson. So X is irreducible, reduced. Affine Poisson scheme. And then the theorem of Ginzburg says the following. So with this hypothesis, assume furthermore that X has finitely many symplectic leaves. Then for all primitive ideal of A, which means that I is an annihilator of some simple left module in A, then the corresponding associated variety is irreducible. So the zero locus of Greux I is irreducible. And moreover, this is a consequence, and moreover, in this case, naturally, it is a closure of some symplectic leaf. Okay, so he strongly uses the previous theorem because, in fact, what he gets naturally is symplectic cores in some sense, and because they coincide, he gets this. And so, in particular, this theorem, we recover from this theorem the famous theorem of irreducibility property of primitive ideals in associated primitive ideal of the enveloping algebra of a simple Lie algebra. But this theorem was proved much earlier than Ginzburg's theorem. It was motivated by other family of examples, but this is a generalization of this one. And we will be inspired by this result in the setting of vertex algebra, as we will see now. Okay, so this is what I wanted to mention about this classical, in some sense, setting. And now I would like to explain the construction in the setting of Poisson vertex algebras. Okay, so Poisson vertex algebra. So, okay, maybe I give a not complete definition, but I think I should at least say what is Poisson vertex algebra. So let's start with a differential algebra. So this is a unital commutative algebra. Equipped with a differential delta. All right, and we say that in this case that V is maybe I should say that this is equivalent to saying that V is a commutative vertex algebra. This is the same. V is a commutative vertex algebra. And then it's a Poisson vertex algebra if, moreover, there exists a bilinear map V O times V to this polynomial in formal variable lambda, So I write the image here like this, as we call it a lambda bracket. So A lambda B. So this is, okay, I write like this. So I write this polynomial like this. And so here, this belongs to V. So AN is an endomorphism of N, and it acts on V like this. And then plus some axioms that I'm not going to list here all, but which are similar to sesquilinearity, skew symmetry, and Jacobi identity. So for instance, yeah, number of axioms. So maybe I just, yeah, sesquilinearity, skew symmetry, Jacobi, and etc. And then, for instance, we can write the left Leibniz rules. So this can be written like this. It must satisfy that for all AB in V, the lambda bracket A lambda BC must be equal to what you expect. Ah, sorry. Mm-hmm. Okay, and then in particular, this implies that AN acts as a derivation on V. So in this sense, you have finitely many Poisson brackets and then finitely many families of derivation. Okay, so maybe I don't list all axioms on this style, but you can expect such axiom. Is it okay? Or just a boring definition, but okay. And then, as I said, there are interesting objects in itself, but also the motivation comes from the fact that to any arbitrary vertex algebras, you can construct canonically Poisson vertex algebra by considering the graded space. All right, so now together with this definition, I would like to explain the notion of Chiral symplectic leaves. So it's exactly the same construction as before. You have a notion of Chiral Poisson ideals. It is what you expect. It is when it's stable by this derivation for all A. And then when you have ideal in the commutative sense, you have the same notion of bigger Chiral Poisson ideal. So it's really the same construction. So Chiral.
There's a question in chat which I also had. Is it now a finite sum or infinite sum? The sum of our lambda, is it from a power series or is it polynomial ring?
Here it's polynomial because it's part of the axiom that A and B must be 0 for n big enough. Mm-hmm. So the level where it becomes 0 depends on A and B, but it is part of the axiom that what you get is a polynomial. Mm-hmm. Okay.
And you said for Lie algebra, there's an example.
Typical example. Maybe I can give a typical example right now. Yeah, typical example. Maybe I give right now the example. But I don't know whether you are familiar. So, typical example I gave is before, but okay, let's say maybe more general. So let's consider a fine scheme. Okay, maybe, sorry, that's not what I want to say. So yeah, to answer your question for Lie algebra, I don't know what you mean, but the example I gave in the introduction is an example of Poisson vertex algebra. But maybe to explain the Poisson structure, it's better to view this as a coordinate ring of arc space. So I don't know if you are familiar with this, but in general, if you have a Poisson varieties, you have a natural Poisson vertex algebra structure on the arc space, so that the restriction, so which means here lambda is equal to 0, gives a Poisson bracket. So it's not really, on the other hand, in this case, it is interesting, but you have, because you have also a Poisson bracket structure on what I want to say. You have also a Poisson, I don't know what is your question, but it is not the same as the Poisson algebra structure coming from the Poisson bracket of G, the formal power series of G. You see, to any algebra, to any Lie algebra, if you consider the coordinate ring of the dual, this is a Poisson algebra. So in particular, this is a Lie algebra with some bracket, but it is not the same here. It is what I'm saying. So I don't know whether it was your question.
So V in this case, is this coordinate ring of this arc space? That's the V?
Sorry?
The space V in this case is what?
Ah, yeah. So the space V in this case, it's a coordinate ring.
Okay,
Yeah. But okay, maybe I can give a more general example. What I'm saying that now let's consider any affine scheme. So first of all, you can consider the arc. So let's say this is R. Okay. And now you can construct a differential algebra. So, okay, I consider the jet of this. So first of all, you consider coordinate ring with infinitely many variables here. And then you have naturally a differential algebra here, sending. So you declare that the derivative of xi minus j is equal to j. Okay, I'm not sure of the normalization, but xi minus j minus 1 for j greater than 1. So this gives you a differential algebra. So first of all, this one is, for the moment, just a commutative vertex algebra in this language. And then, of course, if you now take care of the ideal here, then the jet of R, you take the derivative of Fi. Okay, so this is a general fact that in this way you construct commutative vertex algebra, and this gives you the arc space of X. So this is by definition the spectrum of this. But moreover, if X is additionally a Poisson variety, if X is Poisson, then there exists a unique Poisson vertex algebra structure on G infinity of R. So it's really the coordinate ring such that A lambda B is equal to the Poisson, the usual Poisson bracket if A and B are in R. So in other words, you have that A and B is equal to this times the Kronecker symbol here. Okay. Okay, so this is typical example, and in fact, it's not completely only an example. As we will see, I don't say that all Poisson vertex algebra are of this form, but close to be that. It is what I want to say somehow. Okay, so I want just to finish, just to explain what is Chiral symplectic leaves, but I already mentioned that it is defined in this way. So Chiral stands for its fancy name for vertex. So here you have V. V, it's any Poisson vertex algebra for the moment. And then you take, for any commutative ideal, you take the similar as before. You consider the biggest Chiral Poisson ideal contained in I, and then you define similarly for x in the maximal spectrum of V. You say that x is equivalent to y if P of Mx is equal to this. All right, and then you have a stratification of your Poisson vertex algebra. Sorry, not of the Poisson, of the scheme corresponding. So yeah, maybe I don't know how to write. Maybe spec. Maybe I take the reduced scheme. Okay, and as I say here again, we expect that this is the finest algebraic stratification in which the Chiral Hamiltonian vector fields are tangent. This is the feeling of the construction. Okay, so I already gave an example. And yeah, maybe I can give another. Yeah, but it's very close to this example. Yeah, and if you don't know this example, okay. So maybe I state our main result about this. Yeah, maybe before that, I would like to make a few remarks. So first of all, yeah, maybe a few remarks is that if I consider again the setting of R space, so if I am, as before, X is Poisson, as before, then in terms of Chiral symplectic leaves, we have the nice property that the jet of the Chiral symplectic cores closure is the same as the symplectic cores closure in the sense of Poisson vertex algebra if X is an element of X that I embed naturally in the R space. But this is not the only symplectic cores in the R space. So I mean by that in the R space, they can have, exist some symplectic cores not coming from X, of course. But at least those coming from X are, it fits well with the R space construction. Okay, so now I would like to explain that this can be used to understand general vertex algebra. So now I would like to go to the setting of vertex algebra. So application. To vertex algebra. So here again, I don't give a full definition, but let me recall that a vertex algebra V is a complex vector space equipped with maybe first equipped with a distinguished vector called usually the vacuum, and then a bilinear map. So here I go to the space of the fields here. Yeah, maybe I write like this. So here it's my notation for V tensor, the field of the ring of formal series, A to A times B. I associate, so this is my notation for this series. So you see here N is in Z, and then you have this. So here, this means that AN is naturally an endomorphism of V, all right? And here again, so you remember before you asked me why it's polynomial. So this part of the axiom, and here again, part of the axiom is that AN B is 0 for n big enough, because I ask that the number of terms in negative power are 0. So this is part of the axiom. And then there are other axioms that I don't explain here, but in particular, you have a translation operator. There is a translation operator, which is a linear map of V, which is in fact explicitly in terms of the previous data, which is A-2 applied to the vacuum. But part of the axiom says that this must satisfy that the partial of A, the field associated with partial of A, acts as a derivation. So this is a derivation of AZ. All right. So in fact, the first connection is that V is commutative if and only if, maybe I mentioned this remark, V is commutative. So as I say, it's the same as differential algebra, if and only if A and B is 0 for all positive n. And then in this case, this partial, so this translation operator acts really as a derivation with the product. Well, maybe I mentioned this. And if so, then this acts as a derivation on the product given by A-1b. So in this case, you recover a differential algebra structure. But in general, there is no natural product like that. Okay? So, and as I say, any vertex algebra is naturally filtered. Maybe I don't give the definition of the filtration, but is naturally filtered. I just maybe denote by VP, V the filtration. And an important fact is that the corresponding graded algebra is a commutative vertex algebra, but also a Poisson vertex algebra. So here I don't explain the structure, but it's similar to the fact that when you have a filtered associative algebra, such that the corresponding graded algebra is commutative, it's naturally a Poisson algebra. And here it's similar techniques to show this. And on the other hand, it is what I explained in the introduction. You have this easier functor, which give a Poisson algebra. So on the other hand, you have this quotient, which is, okay, I did not by C to V, but in terms of filtration, it's just the first part of this filtration. Maybe I can say here what is F1V. Here, in fact, the first term of the filtration is the vector space generated by element of this form, A-2B with AB running through V. And then this is naturally a Poisson. This is naturally a standard Poisson algebra by, so the product is given as follows. The product, I denote with the bars the image in the quotient. This is the image of the previous product, and the bracket is given by the image of 0, like that. And the unit vector is given by the image of the vacuum. All right, so now, to your vertex algebra, you have two canonical Poisson vertex algebra. You have, first of all, this Grevy. Maybe I like to denote. Now, first of all, you have the arc space of RV. So RV is naturally a Poisson algebra, usually finitely generated. Maybe I assume this for the talk. And then you consider the arc space of this. I explained before, this is a natural Poisson vertex algebra. Secondly, you have this Grevy. Sorry, I would like to write like this. You have this Grevy, which is also a canonical Poisson vertex algebra attached. And there is a statement by Arakawa saying that, in fact, it's Hai-Shengli, but the fact that it is also Poisson vertex algebra morphism is due to Arakawa. And here you have a Poisson vertex algebra morphism, which is surjective. So in other words, this means that the scheme associated with Grevy, so I take, I can take as a scheme, I prefer, is contained in the scheme associated with this arc space. So in other words, the arc space of XV. Okay, so here XV is by definition the scheme associated with RV. So maybe I did not with tilde, and I did not by XV the reduced scheme associated with that. Okay, so you have in general this inclusion. So unfortunately, the equality is not true in general. We recently we discovered the counterexample quite recently. But our statement with Arakawa is that at the level of topological space, they coincide, at least assuming that XV has finitely many symplectic leaves. So it's close to Ginzburg result, and we hope to use this to prove the irreducibility in this setting. So this is our first application. So I'd like to, I think it's time to mention this. So our first result about using this notion, so it is an application of the notion of Chiral symplectic leaves, it says that if XV has finitely many symplectic leaves, then the spectrum of Grevy coincide with the arc space of XV as topological space, as topological spaces. Okay. So in other words, the kernel of the previous map is contained in the radical of 0. Okay, and second, so this is a direct consequent for direct. It's close to what I explained about symplectic cores in R space. Each irreducible component of maybe I did not this by single. This is usually called the singular support of the vertex algebra. Is in fact a symplectic cores closure, and namely it is the arc space of the symplectic cores closure, which is in fact here the same as symplectic leaves by Brown-Gordon result, and this is the same as some symplectic cores. And here I would like to mention that maybe I add something here. It's of this form, and here recall that if X satisfies this condition XV, you have the irreducible components, which are closure of some symplectic leaves, each time. So this is the irreducible component of XV. And then what our result says that we have the same at the level of a singular support. And in this setting is not obvious because our scheme is not Noetherian, but still we have finitely many irreducible components, and still the closure is a closure of some symplectic cores. This is the statement. All right. So yeah, so a corollary of that. Okay, maybe as I say, our initial motivation our initial motivation was the following conjecture, is that we conjecture that under the previous assumption, so if V, I assume also that V is simple as a vertex algebra, but this is not important, and XV has finitely many symplectic leaves, then XV is irreducible. All right, and then so as you see, this is a statement very close to Ginzburg result, and because we would like to adapt Ginzburg proof, we choose the statement of Brown and Gordon and technique of Gaber-Vaughan on micro localization, we would like to do the same, and this is the reason why we wanted to prove the same result. But now I would like to give also a corollary of our result. So this, I don't explain how we want to attack this conjecture because it's still conjecture. But the corollary says the following: assume that xv tilde, so I recall that this is the spectrum of RV, is reduced, smooth, symplectic. So in other words, xv is just one symplectic leaf. Then we can show in this case that V is simple as a vertex algebra. So a nice example is the following. You take X smooth and projective variety and you consider the global section of the Chiral differential operators on X. So if you don't know what it is, it's just a Chiral analog of the algebra of differential operators on X. Okay, this was constructed by Malikov, Shetman, and Ventrop. And then it is known that the corresponding associated variety, if you can imagine, if you have in mind the diagram I draw, this is just a cotangent space of X. So if you remember the diagram as before, you have this vertex algebra. Here you have the arc space of this cotangent bundle. The zoo algebra here is just the algebra of differential operators, and here you have the coordinate ring of the cotangent space. Okay, so this is well known to be smooth and symplectic. And then the statement says that this one is actually simple. And this was conjecture for a long time. And here, using this notion, we got it directly. Okay, so unfortunately, I don't have so much time for examples. So let me give just one example, and then I'm not sure about Slodowy's slice. Yeah, maybe I explain the application of Slodowy's slice because it was in the title. So maybe it's better to give application to that. So maybe I finish with an application to W-algebras. So the application is about, to be precise, application to the Poisson vertex algebra center of the arc space of Slodowy slice, but this is closely related to W-algebras. Okay, so the statement, yeah, actually our very first motivation was this, because, yeah, I will explain later, but this was some error in some paper and we wanted to correct, and then we find the proof to correct it. So let me state the result. So, okay, so here G is a simple Lie algebra over C, and I consider the quotient morphism. Okay, I assume that it is the Lie algebra of the agent group. Let's say like this: the quotient morphism. So this is by definition the spectrum of the coordinate, so invariant algebra of G. So it is well known by Constant that this invariant algebra is a polynomial algebra. So this is a result of Constant. And here L is the rank of the Lie algebra. So this is a polynomial algebra. So in other words, this is just an affine space of dimension, the rank of G. And the quotient morphism sends an element in X to P1 of X, PL of X. All right. And now I consider a nilpotent element. So this is a nilpotent cone So N is by definition the scheme associated with the augmentation ideal of this algebra. And it corresponds as a variety, just a set of agent nilpotent element of G. And now, so I pick a nilpotent element here. And then I consider the corresponding SL2 triple and the corresponding Slodowy slice, which is by definition F plus the centralizer of E in G. And this is well known to be transversal to the nilpotent orbiter of F. Oh, I have no battery. Sorry, I have to just change. Okay, it's okay. So this is transversal to the nilpotent orbit of F. And the Poisson structure comes from the Poisson structure on the dual of G by Hamiltonian reduction. Okay. So this is a Poisson Poisson affine variety. Okay. The Poisson structure comes from the dual of G. Okay, and what I want to say is that now let's say this map is psi. So this is a quotient morphism, and I restrict this morphism to the Slodowy slice. Let's say psi F. And it is known by, I think is due to Premet or Ginzburg-Premet. So this is a surjective faithfully flat morphism. And then this map induces a map at the level of arcs now. So now the two maps, actually, you have the corresponding map for the jet of G. So a priori, I consider here the jet of this quotient, but because it's affine space, it totally makes sense. There is no problem. But now there is a very deep result that's saying the jet of the quotient is actually the quotient of the jet. So let me explain what I mean by that. So in fact, the arc space of the group acts on the arc space of G, and then you can define the corresponding scheme associated with that. And the statement is that this is still polynomial with infinitely many variables, and this is precisely the jet of the previous quotient. So this is a very deep result obtained independently by Bellinson-Drinfeld, Feigin-Frenkel, and Reis-Tovel. And so here we deeply use this. Okay, and then again, I can restrict to the arc space of Slodowy slice. Okay, so I get a map. So here, okay, this is surjective and this is still surjective. Okay, so the conclusion is this. Okay, so now I would like to connect to what I explained before. I have Poisson things everywhere. So for the moment, it's at the level of scheme. So now I consider homomorphism. And then I have a map from the coordinate ring here, which is this. And this is precisely the Poisson center of the coordinate ring of this. And this is exactly the Poisson vertex algebra center of this object. And then I have a map into, so a priori I go to the coordinate ring of Slodowy slice. So this you remember from my typical example of Poisson vertex algebra. This is a Poisson vertex algebra. And in fact, it goes also to the center. This is easy to see. So in fact, we have an embedding. And our statement is that this is actually an isomorphism. And this is nice because then this corresponds to the graded algebra of some vertex algebra famous, which has a corresponding W-algebras. And this was claimed in a paper of Arakawa a long time ago, but with small problem, big problem actually. But Now we have a deeper proof because we have also the commutative version of that. So it's even better now. So, okay, I finish with this theorem and comment a little bit. So this was our real motivation to repair this. So, okay, the last thing I want to state is the following. We have that, in fact, this is not only an embedding, but an isomorphism as Poisson vertex algebra. Okay, so as a Poisson vertex algebra, and moreover, this is the center is free. No, sorry, this is free over its center. It's free. So this Poisson vertex algebra is free over its center. Okay, and this implies, so I'm sorry that I haven't explained at all this, but this implies that the corresponding W-algebras, so this is just W-algebras associated with G and F at critical level. So level is some parameters, and here this is minus the dual Coxeter number of G. All right. And this is a quantization of Slodowy slice in the sense that the graded algebra is this one. So here we get that this one is free over its vertex algebra center, and for all nilpotent elements, and also the center vertex algebra center is the same as the vertex algebra center of the affine vertex algebras of this. So maybe here I explain some notation. This is obtained by BRST reduction from the affine vertex algebra attached to V. And if you don't have feeling of this, maybe I can say at least that the graded algebra is precisely the coordinate ring of Slodowy lines. All right. And this, in fact, you can put any level K. Here, maybe I put K, so maybe I put K. Okay, and why we put the critical level? Actually, non-critical levels, all these centers are trivial. And here, the center that appears here, when, sorry, here K is of course the same level, is critical. The center that appears here, it's known to be the Feigin-Frenkel center, and it's a very big, in fact, it's a polynomial algebra, infinitely many variables, and roughly it's you take infinitely variables coming from the PI here. And this play a very important role in representation theory. And so our result generalized two results. So remark, and then I finish with that. So this result was known in two particular cases. In some particular cases. So first of all, by Feigin and Frenkel, they consider in fact the case where F is regular. But in our result, we don't need to assume this. So this means F is in the regular nilpotent orbit whose closure in the nilpotent cone. So what they prove is precisely that the center here in this case is the same as this Feigin-Frenkel center. And on the other hand, Frenkel and Getzgery proved the statement of freeness for the universal affine vertex algebra, and this corresponds to the extreme case where F is 0. So this the freeness was obtained here, that this one is free over its vertex algebra center. So in other words, our result is a generalization of these two results. And this, okay, I haven't explained at all, but this use Chiral symplectic cores, but maybe I don't explain this. Okay. Okay, maybe I finish with that. Yeah.
Oh, thanks a lot. Yeah, do we have questions? And just speak up if you have a question, please.
Yeah, I have a question about, so at some point you talked about Chiral differential operators on projective varieties.
Yeah.
And you mentioned that this recovers the cotangent space of the symplectic variety of the projective variety. So what is the exact statement that, so global sections of CDO is what? Like, how do you recover the cotangent space of a projective variety?
Oh, okay. Where was it? Do you still see my tablets?
Yes.
Okay. So, but do you see when I move my tablet?
Yes.
Okay. So yeah. So here. So it's about the diagram.
Yes, exactly.
Yeah. Okay. So the diagram I wanted to explain is because before I explained that we have starting from a vertex algebra, we have taking the graded algebra, Poisson vertex algebra. And then we have this Zoos algebra. I haven't really talked about this in this talk, but just to mention canonical object attached to this vertex algebra. And here we have this Poisson algebra RV. And in this case, the diagram commute, and what I wrote here is just the corresponding element. So here, maybe I don't define the Chiral differential algebras because it's a bit technical, but just to have a feeling, the corresponding graded space is the Poisson vertex algebra, which is, it's because here there is a typo. It's arc space of cotangent. It was a problem.
I see.
Yeah,
There's also the notion of associated variety of a vertex algebra, which I was wondering if you could maybe make a comment about. Like,
So here, in this example, the associated variety, even as a scheme, is a cotangent bundle. It is what maybe I wanted to mention here.
Or maybe the affinization of the cotangent bundle, because is it the cotangent bundle itself or the affinization?
Sorry, I cannot. It's a bit.
Okay, let me just repeat. The associated variety is always affine. Is that right?
Yeah, that's right by construction, because here you remember RV I defined as a quotient here, and by definition this is the scheme associated with RV. In general, it no need to be finitely generated, but in most examples we consider it is.
But T star X, if X is smooth projective. Oh, do you mean?
Yeah, okay, maybe here, okay, this is badly written. What I want to say is rather, okay, the exact things I should say. Yeah, in fact, you don't need at all projective, but okay, if you can do projective if you want, but then I have to write differently. In fact, it is a sheaf of Poisson vertex algebra. Sorry. But I can assume, yeah, you can put affine if you want, but if I want to state like that, maybe I put, okay, then it does not really make sense in this way. Then in this way, I have to say, this is a sheaf of Poisson vertex algebra, and this is a sheaf of Poisson algebras, and so on.
Okay. Okay, but if I just take the associated variety of this global sections of the CDO sheaf, then you get the affinization of T star X. Is that what you get?
Yeah.
Okay. Thanks.
Yeah.
All right, any further questions?
Can I ask a very naive question?
Yeah.
So for a given Poisson manifold, there's a notion of sheet, right? You take the locus where the rank of the Poisson structure equals some constant, and you take a irreducible component of that. Can you comment on how the notion you defined today is related to that?
Can you tell it again? Notion of sheet?
Yes, I mean, you fix a constant and you take the locus where the rank.
Yeah. There is also a stratification between by rank, and this is related. In fact, you have, okay, I don't want to say mistake, but you have always inclusion between symplectic core, symplectic leaf, and this rank stratification. Yeah, I don't want to say mistake, but yeah, there are connection between the three stratification.
Okay, thank you.
Yeah, and also, yeah, I should mention, but this is natural, but these symplectic cores are designed so that element in the Poisson vertex center, if I consider symplectic cores, are constant of this, of course. This is designed for that.
All right, any further questions? Well,
May I?
yeah, please go ahead. Please go ahead.
Yes. Hi. Yes. So if you take a graded, non-negatively graded vertex Poisson algebra, say V, and you truncate it at level 1, so you just keep
non-negative Poisson.
It's a graded. V is a graded space, right? So in the vertex Poisson algebra has an underlying graded vector space. So V. So if you just take V0 and V1 and look at the operations that survive, that's actually the -1. Then what you get is a current Dorfman algebra. It's basically a current algebroid. Basically the same thing. And conversely, given any such, you can freely generate the vertex Poisson algebra from that. And so, yeah, there's this kind of adjunction. So my question is, so if you take some current algebroid, then what will these symplectic leaves look like?
This I don't know, but just to be sure, so here instead of taking the quotient, I consider you just divide by this differential A, that's correct? So you have an inclusion, I think, when, is it correct? You just divide by partial A or something like that, is that correct?
No, you don't truncate at level 0, so you have what remains of that differential, right? So it just goes from V0 to V1. And then you have these, well, like what survives of the lambda bracket.
Yeah, I see.
So that's what you get is pretty much precisely these operations will satisfy the axioms of a current algebroid. So you have a algebra, a module over it, and then a bunch of these operations. I don't know. Are you familiar with this?
No. This I don't know. What it's happened in this case, I don't know.
Okay. Well, yeah, I was just saying that it would be interesting to to look at the. I mean, it's like this is a very rich supply of Poisson vertex algebras that you get this way, and would be curious what what the symplectic leaves that you construct will look like in that. Yeah, in that case, in those cases. So one example, probably very simple, where like the most basic example, where this V0 is just C. So it's just 1 point. What you get is just a Lie algebra with an invariant inner product. So what do you maybe know what the symplectic leaves would?
I have a question.
That?
Who is talking?
Oh, I'm sorry. Let's see. Am I not? It's Dima
I
Reutenberg.
don't know who is asking questions.
It's Dima Reutenberg.
And now I see all questions on the chat. Sorry.
Yeah, that's
Okay, sorry.
yeah, what I'm saying now is related to what I wrote in the
I
chat.
see.
But let's say, but let's even restrict to that, to that specific, special case when the base is a point. So it's just, so it's basically just get a Lie algebra with an invariant inner product. There are many such Lie algebras. So, so you can generate the vertex Poisson algebra from such a thing. So what will the symplectic leaves look like in that case?
Okay.
So is it one of the examples that you already gave? I'm just wondering. It's like you gave some, some examples constructed from Lie algebras, but I just didn't see the inner product there, like the killing form or anything like that, where it would play a role.
Probably it's the example that's visible right now at the very last line.
Let's see, is that what we're looking at now? So I can see that very well. The theorem of Frenkel and Gates-Goury.
I don't know. What is the question? I'm lost. What was your question? Actually?
Oh, so if you have a Lie algebra with an invariant inner product, and you can construct a Poisson vertex algebra from that.
Yeah.
And so what are then the symplectic leaves in the sense that you've been explaining?
Yeah, as I say, the one coming from the base that we understand. So this is arcs of symplectic cores, but in general, there is no reason to be of this form, and this we don't know so well.
So, but what does the killing, well, the invariant inner product, does it show up anywhere in any of your constructions, or is everything determined just by the Lie algebra structure?
Yeah. I'm not sure I understand your question. I'm sorry. Maybe we discuss after. I don't know.
Okay, that's all right. Thank you.
Right. Any further questions? If not, then let's thank Anne again for a very instructive talk.
Thank you.
I believe next week's speaker is going to be Simon Gut.
Okay.
Well, thanks all for coming.
Okay.
And hope to
Thank
see you
you.
next week. Bye-bye.